All right. So this is talk about human AI, and in one version of the world is like I think this is in fact the dominant view of AI in the world currently is to think about how we can pursue intelligence and by making the AI stronger and stronger. And this path can potentially lead to a world that some of like people who are older in audience might have seen this movie, and it could be a world that's similar to the Matrix, where people are used as batteries and AI is this powerful agent that dominates the world. And that is the world that I kind of like want to advocate against. And in general, there starts to be this community called human-centered AI, where the focus will shift from emulating humans to empowering people. And this is a book by Ben Steinman out of Maryland. And one kind of very stark difference from the previous picture is that in this one, you actually see people. And you don't see the AI as the main thing. And in fact, a lot of the technologies are so well embedded that you don't see them as a striking object in the world envisioned by this book cover. And in particular, in this talk, I'm going to advocate a particular view, which I now sometimes call complementary AI. I think the idea is that we think of human as a puzzle piece or like an incomplete puzzle piece. And we want to build AI to complete this puzzle. And if we ask GPT-4 DALL-E, this would be like one version of GPT-4 imagined kind of how this complementary AI could work. But the important piece is to recognize that this version of the brain has an important missing piece in the middle. And we kind of try to build AI to fill in that piece. And that metaphor will come again during the talk, especially at the end. And in particular, we are thinking about a particular set of problems, which we call decision making. How can we effectively develop AI to support human decision making? Decision is a very overloaded word. So before I proceed, I'll try to clarify what I mean by decisions here. By decisions, I mean cases that are very common in our society right now. And for instance, in the first one, recidivism prediction, where a judge can make a decision on whether a person can be bailed or not. And similar scenarios happen a lot of in the civic system. And medical diagnosis, oftentimes the doctor needs to see for instance, a person's medical record and decide whether the person has cancer or certain kind of disease, or design certain kind of treatment. And finally, this final image is a little bit opaque, but I think it represents the case of like hiring or admission. In general, you are looking at a candidate and then decide whether you want to hire this candidate. And in all these cases, you can kind of see that all the decisions actually reduce to the pretty simple prediction problem. You're given some input, you want to decide whether a person should be released for bail, whether someone has cancer, or whether someone should be admitted. And there's a whole class of policy problems can belong to these prediction policy problems. And if you're interested, you can check out this article for more examples. And those very simple decisions will be the focus of this talk. Any questions or is that ahead? Okay, cool. So for these kind of decisions, especially the examples that I was giving, I think there are a couple of important properties that I want to argue. Like in particular, that humans should be in charge for these decisions because of reasons in accountability, law, and ethics. And in fact, there are some rulings already that have decided that in the context of risk assessment in recidivism prediction, these tools cannot be used to determine the severity of a sentence or whether an offender is incarcerated. And judges be made aware of the limitations of risk assessment tools. And in many senses, I think one of the explanations that we are going to consider in this work is trying to help judges be aware of the limitations of risk assessment tools so that they can make better decisions with the help of risk assessment tools. And it's also the second observation about this decision is that in all these decisions, human decisions are far from perfect. And in fact, I think the reason is that most of these high-stake decisions involve reasoning about complicated social and biological processes with inherent uncertainty. Like when we release a person, technically by law, the prediction should be dependent on your prediction of whether the person is going to show up again on court without being arrested or while on bail. And in fact, there's so many uncertainty in the real world, like maybe the person had a another robber attacking them, or like they encounter a car accident in the middle, or they lost their job because they were incarcerated. There's a lot of different factors that the judge didn't have access to in making that prediction, and that will only happen in the future. And as a result, I think humans usually have their own mechanisms, which can be useful signals, but they often also have biases and preferences in making their decisions. Those are not reliable information, or like those are things that is very useful to know from the point of developing AI. And again, because human decisions are far from perfect, so it's reasonable to think of human as a puzzle piece that's incomplete, and it's useful to think about how we can build AI to complicate that puzzle. And an important part of that is actually to know what the shape of this human puzzle piece looks like. And all in all, this is trying to argue that there are a lot of exciting opportunities in this space for AI assistance, where we put a human in the center and think about what's the best way to support a human in making these important decisions. And there are many different possible ways, and this talk will focus on explanations. Explanations has been a very hot topic in AI or related world, or even in fact in the recent bill of AI, explanation is a big part of the bill. And the general belief is that explanations may help humans make sense of AI predictions and improve their decision making. So there are two important steps. One is make sense of AI predictions, and then the second is improve their decision making. And later I will come back to this claim in more details, but I kind of want to highlight these two parts before I move on. For now, we can just look at how explanations are generated. There have been a lot of different algorithms, and in general, most algorithms for generating explanations ignore humans, both in evaluation and in generation. And I'm not going to go into details of each of these algorithms. And I think that is true even in the stage of LM, since a lot of the phrase kind of emphasize open the black box. And the black box is the only object in the phrase, and your goal is to open it without accounting for who is opening the black box or what you are showing this to. And a lot of this talk is kind of emphasizing there is this important interpretation step after you generate explanations. And without understanding this interpretation step, it's going to be very hard to build explanations that can actually help people make decisions. And that is kind of the general thesis of this talk. And we are going to take it in 3 steps. First, we are going to look at a simple case of human-centered application-grounded evaluation. Then we are going to build a theoretical framework for AI explanation and human understanding. And finally, we'll show you a case study on how to align AI explanations with human intuitions. Let's start with the first step, where we kind of show an example of human-centered application-grounded evaluations. There has been a lot of work in this space. I'm just going to show you like relatively old one from my group, and I think is indicative of what's going on in this area. So this task is to decide deceptive reviews. So that you are seeing a review and you are deciding whether it's genuine or deceptive. By genuine, it means that it's written by someone who actually stayed at the hotel. And deceptive means that this was written by someone who never stayed there, was just paid to write a review for this hotel. And this review, I'm just going to read it quickly, and then I will ask you to make a judgment. There's no stake here, and in fact, I'm not really interested in that question, but it's great to get you involved. My stay at the Talbot was a wonderful experience. The service at this upscale hotel was beyond my expectations. The Gold Coast location is close to Michigan Avenue, the museums, and many of the other sites Chicago has to offer. If you are visiting Chicago, I highly recommend the Talbot. Raise your hand if you think this review was written by someone who actually stayed at the hotel. Good. I guess in general, I think it's good that everyone votes. So, but I see about 2 or 3 hands for this. Raise your hand if you think this was written by someone who never stayed there. So I think most of you think that this was written by someone who has never stayed there. Now, this is a common way that, like I said, that question was not in particular the question that I'm interested in. This is what I'm actually interested in. So these are some explanations that we show for this question. And in these cases, we are just highlighting important words for the model to make its predictions. So the model somehow thinks Chicago is very important. Seeing these explanations, did any of you change your prediction? Or what do you think of the explanations? You can keep that to yourself, but if you like to have a conversation, I'm happy to have that too. But in most cases, people just shake their head, which is the reaction that I'm looking for. And similarly, right, like I think this is another type of explanation where we show two examples. One is a deceptive example, one is a genuine example. And again, like I think the reaction I'm looking for is that these explanations are not at all useful. We did a lot more study in this work. We kind of had a whole spectrum of different possible assistants that we can provide, and then we look at human performance and trust. So I'm only going to focus on human performance. And in the end, what we found was that humans are terrible in this task, but this audience is different. All of you were great. That review was indeed deceptive, and most of you were able to recognize it. I guess you are very unique for that at this particular example. But in general, most people, when they look at such examples for many repeats, their performance is about chance, and AI can easily get above an 87. And here are how different assistants may change people's decision. And in general, like if you're interested, you can dive in the paper for more details. But I only want you to take away for a very simple message: human plus AI in these cases is worse than AI. And this story is actually like very common in a lot of these decision-making settings. There have been a lot of papers that have found similar things. If you have a human performing at a certain performance, and if you bring AI to help a human, and usually that means the AI is pretty good. And in this case, AI is better than human in terms of measured accuracy on a test set. Again, that's a kind of very complicated statement to make, to argue that AI is better than human. But in this, we have a quantitative measure to show that AI is at least better on these sets. And then human plus AI will bring human up a little bit, but still worse than AI. And in many ways, that is not an ideal outcome that we want. And that's kind of the starting point of like the rest of the talk, or like that's the puzzle that I have been trying to make progress towards for the past few years. And if you're interested in more of this kind of work, we have a survey paper, or like we also have a tutorial to kind of start to talk about the best practices in doing this kind of human-centered evaluations. But for this context, we can just stop here on this general problem. Of course, what we ideally want is to be able to have human AI teams to be able to outperform both AI or human. And there are many possible conditions for this to happen. And I'm going to only touch on a little bit about explanations. But if you like, I think in general, I think this human AI complementarity problem is the most important problem in the context of human-centered AI, in my opinion. And if you are following alignment or the recent AGI discussion, I don't know, even in that context, this problem also shows up sometimes as a different name, sometimes known as scalable oversight. So the key problem is to think about how a person can supervise AI that's better than themselves. How a person can decide AI whether of nominally better accuracy, whether the AI's prediction is correct or not. That's kind of the essential question behind all of these discussions. All right, so the first part is to try to convince you that human-centered evaluations reveals that the current explanations fail to improve human decision-making. So we actually tried a couple more times. I guess I was kind of naive. I was just hoping that this was just one case failure. So I tried a couple more experiments. Most of the experiments still showed the same thing. So I decided that maybe I shouldn't try it more. So I started to think about what is really going on. So we wrote this article called Machine Explanations and Human Understanding. And in fact, we were not very successful in our work in human AI decision-making. But that's not always the case for explanations. There has been, even in the very earlier work in Lime, they showed that feature importance can help improve model debugging. So what's going on? I think what is going on in these mixed results is that we're actually trying to achieve very different things. So it's important to think about what we are trying to achieve with these explanations. And under what conditions can explanations improve human understanding, and in which way? So we kind of earlier I mentioned that we have surveys, so we kind of choose the subpart where those has explanations and dive into these papers to look at how they measure human understanding. And in general, there are three types of concepts of human understanding that they try to study in this work. And using this very simple classification problem as an example, this dashed line is a true task, and the model, the solid line is the model. So like, I guess the animation actually get ahead of me. So the dashed line here, it shows the boundary between true positive cases and true negative cases. And we call that a task decision boundary. And this solid line shows model decision boundary. And if you are good with variable names, it's good to remember F and G, but I will repeat it again. And this yellow region shows model error. We use Z to represent the function, but Z can be inferred from F and G. And all the existing quantitative measures of human understanding can map to one of these three concepts. And like, for instance, like a lot of times people try to look at a human plus AI performance, which is what we did earlier. There, we are interested in task decision boundary. Sometimes people ask whether a person can simulate the model. And in that case, you are looking at a model decision boundary. And sometimes people look at trust, and usually that's in the form of model error. And then we, given that insight, we try to build a formal framework that describes the interaction between AI explanations and human understanding. So to formalize this, I'm going to move to this local version, which is a reduced version. Essentially, given a particular instance X, Y is the true label of these instances, and head Y is the model prediction. And all actually, just for context, in most of this talk, we assume that we have a given model. And then Z is model error. And in the real world, for the actual variables, Y and Y hat can determine Z, because if you know the true label and know model prediction, you know the model error. But what we are interested in is not this real world. What we're interested in is the human understanding of these variables. And for human understanding of these variables, we add a superscript on top of each variable. So YH refers to human understanding of task decision boundary. In other words, it would be what a human would have predicted for this instance. And Y hat H is what a human thinks that a model would have predicted. And a priori, we don't really know the relation between human understanding. I think that's kind of the main puzzle, or like main thing that we're trying to clarify in this framework. And we have to make assumptions to be able to get a better graph, get a more useful graph between these human variables. And a lot of this paper or this work is think about what assumptions that we can make. And we actually introduce some like new knowledge in terms of like writing causal graphs, new language in terms of writing causal graphs. Just to walk you through one simple example. Here is the case where we show the show variable. You can think of as literally show you the variable, but sometimes it's not necessarily like showing that. For instance, in model prediction, show Y hat just means that I show you the model prediction. Then in that case, the prediction will set your human understanding of the prediction. You now for sure know what the model predicted for this case. And show Y is often impossible because you don't know the true label of the case in a lot of tasks that we are interested in. But often cases in AI tasks, we actually work on tasks where human generally know the label. For instance, if you replace deceptive prediction, review prediction to sentiment prediction, then in most cases, you can assume that humans reading the review knows what the true label is. So you also have Y. And this is actually like this very common graph in model debugging, because in this case, a human, by knowing Y hat H and YH, or the better way to say it is by setting Y hat H to Y hat and YH to Y, the human now knows whether the model is correct or not. Then they can debug. But that's not always the case in other contexts. And the main result of this paper is this theorem where we argue that when predicted labels are shown, for instance, X, expression E that's derived only from the model itself, like the explanations that are only about opening the black box, cannot improve human understanding of the task decision boundary or model error beyond the improvement from showing predicted labels. That's quite a mouthful, but like to simplify it, roughly what we are arguing is that without assumptions about task-specific human intuitions, how human in particular is solving a task, we cannot improve model decision. We can improve model decision boundary with explanation of model predictions only from G, from the model itself, but we cannot improve task decision boundary and model error. We need something more than the model G to achieve those two goals. And this is a problem because, like next, I'm just going to show you a proof schedule of the proof. This is a problem because in reality, most of the explanations that we have only come from G. And we have a model, we design some algorithm to figure out how can we generate a function, explanation from the model. So this would be the simple view. We have the x, and through g, we get this prediction. Through the explanation function that's derived from g, we will generate explanation. Both of the explanation is assumed to be observable, and for y hat, we are going to have a little different discussion later. Feel free to interrupt me if any of this is confusing. So first, I think these explanations can improve people's understanding of model decision boundary, because this explanation introduces this backdoor, right? If we don't show you this, improving people's understanding of this model decision boundary mostly makes sense if I cannot show you the model, I ask you to simulate the model. Now, by showing you the explanations, I open this backdoor so that as a human, I can kind of get additional information about what the model is predicting by only looking at the explanations. And that's something that explanations can achieve. And this explains why feature importance can improve model debugging, because it can help you understand better about the model's decision boundary. And next, this is a more complicated case where we are going to argue that explanations cannot improve human understanding when the prediction is given. So if I show you the model's prediction, that will already give you some information about what the model is predicting. And now on top of that, if I show explanation, my argument is that you won't really get any additional gain to y and z, which is task decision boundary and model error, these two variables that you are generally interested in our earlier framework. The reason is that because EG comes from G, so that's kind of the main problem, because the explanation function only has access to the model, so it cannot really give you any advantage over this side, which requires access to F. And as a result, G blocked all the possible paths from the new information explanation to F, and as a result of Y and Z. So according to D separation, essentially, if I remove all the dashed variables, this graph are separated. So E doesn't really change the dependence between your human set of variable with Y and Z. Go ahead.
Yeah, I'm trying to understand what does explanation mean in this context. For example, the early example you gave about AI and human predicting whether this one is a fake review or not. What does explanation mean in that scenario?
Yeah, in that case, I think, maybe give me a second. I think, for instance, earlier I showed some feature-based explanation, essentially highlighting some words, right? Now I tell you, these are important words in the model's prediction. So that's one possible definition of explanation. Explanation can also be natural language, but when it gets to natural language, that's where it's a little tricky, to whether, all my proof condition on this graph is true. So which requires that E doesn't have any additional connection with F. But when E is natural language, I think you can still make that argument, but it's a little trickier, and we can save that. But I think when E, for most modern explanation algorithms where you identify important words or identify, for instance, inferential training examples, I think it's very clear that E only comes from the model itself.
So explanation here is about how human understand why machine makes certain decision, or is more about how human understand why human makes certain decision?
It's about explanation's goal is to explain why a model makes certain decisions.
Oh, why model? Okay.
And this argument is to say that explanation, because of in this causal framework that we have, the explanations can improve your understanding of model decision boundary. Can improve you understand what model. For instance, you can improve your ability to simulate the model. Mm-hmm. In the future, if I don't show you any explanation versus I show explanation, you can simulate the model better. Mm-hmm. But it cannot help you better decide whether the person is sick, it has cancer or not, or whether the person should be bailed or not, on top of showing the model prediction.
Okay, so it doesn't affect my judgment on the ground truth, but it affects my ability to judge based on the model decision.
Yeah.
Okay.
So in order for that to happen, I guess this earlier, next I will show more concrete example. Hopefully that helps you understand this better. So explanations need to activate some what I call task-specific intuitions. So there's this magical variable H that kind of describes how human works. And explanations needs to change H variable an edge variable has some relation with some variable in here. And I think the most common path is through model error, which I will explain a concrete example later. And if we, like, I guess there's another magic about this framework, like show operation can actually change the causal graph. That's the important part of how showing a new information can change your, it can improve your decision. And in order for it to improve your decision, you need to add this new path from H to Z, so that now maybe you will know the model error better, and as a result, it can improve your decision. This is just an example pathway, but the argument is that if you don't activate any intuitions from human to the left side, the explanations cannot be useful. Just to consider a very concrete example to illustrate this point. So assume that we are trying to do COVID diagnosis, and we have a chest X-ray. And we consider two cases. One is that users has no task-specific intuitions. So in this case, because users has no task-specific intuitions, there's no intuitions to activate. So this represents the case where there's no pathway that we want. So here, in addition to the prediction, which I didn't show, but the important part is explanation. I show you these two explanations, which is how the model makes prediction. There are many algorithms to generate such saliency maps. And because users have no task-specific intuition, so this is the same as showing this to an alien who has never seen human body. Like I just show you these two boxes, doesn't really help you do anything in terms of deciding whether the person has COVID or not. It can potentially help you understand model decision boundary, because in the future, you know, if the model highlights this part, it will predict positive once you see enough such explanations. So understanding of task decision boundary is bounded by the model decision boundary. The best thing that the alien can do, whether they see the explanations or not, is to follow the AI prediction. But in the other context, if we have users as task-specific intuitions, and in this case, we can think of the specific intuition is that they know where lung is. They know that COVID is something that attacks lung. And in this case, the users, the one possible mechanism is that humans can now use explanations to verify whether the model uses valid information. And in this case, this is not valid information, so they will choose to override the model prediction. And as a result, hopefully it will lead to a scenario where human plus AI leads to better performance than AI. Yes.
Questions about the first assumption. Is your assumption is more like they don't have task-specific intuition, therefore they try to understand, but they cannot understand? Or is it more like because they don't have a prior knowledge on this thing, they're just like give up on trying to understand?
The argument is that they are trying to understand, but they cannot. Because there's no, like, yeah, I think it's easier to describe in the formal way, like it's more in this scenario where I show explanation doesn't really add you to anything on Y and Z, which are the variables that's about whether the person has COVID or not. But you can potentially know better about what the model is predicting. But we kind of, if you assume that we already tell you what the model is predicting, then that understanding is not useful in that context. So I think there are actually like two conditions, just to be super clear, right? I think this is a possible mechanism. But in order for this to happen, it also requires that human intuition is somewhat activated correctly. It needs to be activated in cases that's correlated with model error, right? Like I needed to, when I think the model is likely to make an error given the explanations, the model needs to actually make an error. In that case, that's how humans can correct the predictions. Yeah.
Really silly question. This human plus AI versus AI. Whenever you're talking about AI, you're talking about, for example, you kept talking about the COVID diagnosis. We're talking about a hyper-tuned model trained for that very specific purpose, and you're comparing it to a human, and you said you ran this experiment 5-10 times, and you kept getting the same response, But every time you ran it, you may have used the same human against 10 different AIs, I'm assuming. And every instance of the AI was hyper-tuned for that specific purpose. In other words, you take that AI from whatever purpose it was originally doing, and you put it into another one, it fails spectacularly. Is that accurate?
No, I think that's not, like, I think when I say multiple different experiments, it means that I try different tasks. Well, for each task, I have an AI. Like in general, I think the key message is that you have AI that's reasonably good at this task. And in many cases, better than human. But that's not super important condition. Yeah, for that specific
Until
task.
we have AGI, we're not gonna have one AI who can do everything. For each task, I'm assuming it's a different AI. That's my point.
Yeah, but I don't think that's critical in a lot of what I'm talking about. You can also have an AGI that's good at every task. But the important thing is, since I'm only considering human doing a particular task, so AI's performance in other tasks is somewhat irrelevant for this context. But I do think like that kind of depends on. Yeah, I think that's fair to say. Right? I think I think that's a fair argument. But there's some subtlety that I was thinking about, which if you're interested, we can chat more later on. Yeah.
For the intuitions, I guess it might also has to do with the people's experience level, right? Like for entry level radiologists and advanced radiologists, they might have different intuition, and that might.
Yeah, exactly. That's something I will get to later. I think the important part, like you are getting the gist of the entire talk. Like the important thing is that you understand the human intuitions, and it's totally possible that different humans have different intuitions, and entry level and experienced radiologists have different intuitions, and your explanations should tailor to those intuitions to be useful. Otherwise, a uniform explanation that only explains the model decision boundary won't help them make better decisions. That's exactly the argument. Yeah.
Does human plus AI being better than AI require kind of like human AI complementarity, where humans are better in certain things than AI and vice versa? So I figure otherwise humans are monotonically better and AI monotonically better.
Yeah, that's a great question, right? I think like that's kind of goes back to the like I like the AGI community, how they frame questions. Like the question is like how human can supervise the AI much better than itself, right? I think it requires complementary. It requires complementary at some level, but it doesn't have to be that you have this naive. Like let's imagine this is where human AI make errors. It doesn't have to be that, like say this is where AI makes errors, and this is where human makes errors. It's totally fair that a human always make errors, more errors than AI. Human makes strictly more errors than AI. A human is just strictly worse in terms of decisions. I think even in this case, it's possible to achieve complementary performance through explanations. For instance, in this mechanism that I just talked about, like the human can be strictly worse than AI, but once you have explanations, humans' other intuitions can come in, right? These intuitions, just knowing where the lungs are is not useful to make, is not sufficient for making predictions, but it might be sufficient for recognizing AI errors. And as a result, you can still get a complementary performance simply by being able to recognize AI errors with the help of explanations. Does that make sense?
Yeah.
Great. So going back to what the claim that I made earlier, right? The general intuition for a lot of people who work on explanations is that explanations may help humans make sense of AI predictions and improve their decision making. And I think a lot of what I'm trying to argue is that the relationship between these two parts is very complicated. It's not any making sense of AI predictions can improve their decision making, and we need to think carefully about what making sense of AI prediction means and what is required to improve their decision making. Yes.
I think there was a question from Zoom that they asked, did you try the method or experiment on subjective tasks, for example, detecting hate speech, correctness of a political argument, and those things require human input and complicated threshold. So do you think that human plus AI still is worse than AI itself, or human itself is worse than AI, still applying that scenario, like subjective tasks?
I guess like in general in these tasks, I kind of assume that there is some ground truth that you can reliably measure the performance. And if it's subjective, like one trivial way to define subjective task is that human always has, like whatever human says is correct. Then I guess human plus AI will always be the same as human because you will always have like whatever is produced. I think it's like in short, I think like in general for performance measurement, like I'm mostly thinking about the tasks where like you can actually reliably get good measurements. There's some out of the world ground truths that you are trying to match. That's the scenario that I'm thinking about, and it's not necessarily objective, but it could be like subjective by some other people. Right? You are trying to predict what the judges are going to decide for this case. I think that's still fair, but you are just kind of trying to match different types of approaches. All right, I think just I want to kind of emphasize that this is not just like my own argument in many ways. I think this is a kind of a growing recognition from many different research communities. In fact, like this paper by Raymond Fogg and Dan Weil makes this very strong claim that verifiability is the only possible pathway towards complementary performance, which I think our framework kind of suggests that there may be some other possible pathways, but I do think verifiability is probably the most likely path. All right, so in general, I do think the key message that I'm trying to make here is connecting explanations with task-specific intuitions is critical for improving human decision making. And the final part, we're just going to show a simple case study of aligning AI explanations with human intuitions. So this work last year at iClear, where we show how we can learn human compatible representations for case-based decision support. So now I think, hopefully, I kind of have derived this general recipe for how to build human-centered explanations. I think there are at least 2 steps. First, we need to articulate the mechanism of how humans may interact with explanations. Like, what do you expect if humans use in explanations to improve their decision making, or in general, just to make decisions? And then we generate explanations that tailor to this mechanism. And in this work, we are going to look at a very particular mechanism that is relatively simple to think about. We are going back to this favorite X-ray example, but because we are literally working on pneumonia, so I just replace the name COVID with pneumonia. And we are thinking about how we can help support explaining this prediction. One way to do this is that we have this prediction, AI predicts pneumonia. And one way to do this is to generate a justification or generate another example. And in this case, it doesn't have to be generated. It can be choosing another example as a justification of this prediction. And in this case, in order for, we assume like the person makes decision by deciding how similar these 2 images are. If they are very similar, then they trust AI's prediction. If they are not very similar, then they reject AI prediction. That's how human is going to use the prediction. So with that mechanism, then the story is relatively simple. Similarity between the task example and justification is correlated with model error, is an important component for human to make better decisions by being given this information. And similarity to AI is aligned with similarity to human. This second part is what we are going to focus in this talk. We in order for this to work, we can only choose justification or general explanation based on what AI thinks is similar. That has to align with what a human thinks is similar, which is not always the case. For instance, this is an example in butterfly, and here you can see the model does really well. The blue dots and the orange dots are very well separated. And we have a test image over here. And if we just find the nearest neighbor based on a trained ResNet model, it will look like this. And with some magical way that I will kind of explain more later, we can find a nearest neighbor based on human perception. And you can see that this one looks much more similar to that image based on your human eyes, or actually it's based on my human eyes. And that black one looks nothing like the top image on the test, although they are very close in the space that the model learned. And in this case, like we have a very simple explanation algorithm is essentially KNN, right? Whereas we learn representations, we try to find the nearest example in these learned representations. And the reason that we are not getting human compatible representations is because the representations is not aligned with human similarity judgment. So our solution is to try to learn human compatible representations so that we will have an embedding space or have a representation space that's aligned with how humans would judge similarity between images. And once we figure that out, relatively, the rest of the thing is relatively straightforward. One thing that we did was to, like, there actually has been a lot of work on learning human semantics. And what we did is mostly combining 2 things. One is to collect this kind of data set of human triplet judgments. Given a chest X-ray, we take 2 references and then ask the human to judge which one looks more similar to the candidate image. And once we have this kind of triplet data, then we can have a multitask learning framework. Well, first we have this typical classification loss, and then we have a triplet margin loss to make sure that human judgment is consistent in the representations that AI uses. And then once we have this, and with the first such like chest X-ray human judgment data set, we can then start to evaluate them in the context of decision support. I'm going to show you two related decision support, and there's some subtle importance that's critical for interpreting the results. So this is the explanation. So the envelope stands for explanations. And we show you, we call this neutral decision support. So we don't even show you the model prediction. We show you nearest neighbor in the predicted class and nearest neighbor in the other class. And in this case, is just pneumonia or not pneumonia. And I don't know what it is. I just show you two images. And I ask you to decide which one looks more similar to that image. And this would be one way to support your decisions in the context of like pneumonia classification. And we ask participants to determine the diagnosis based on which support image looks more similar to the original ones. And we consider three different approaches to generate the message. So that's how we evaluate. So we have a random method where we just select a random image in each class. And we have AI, which learn the representation, and then we choose the nearest neighbor in each class. Then we have our AI with human compatible representations. And we also try this on butterfly. So here are the results on neutral decision support. You can see, surprisingly, AI itself actually does worse than random. Somehow AI learns the space where the nearest neighbor is not very well calibrated because it's like to human eyes. And this is very surprising. I'm going to kind of explain this more later to just make sure, like there's still something to unfold in more details, but I'm at least going to show that we are not crazy and AI still learns something. But our human compatible representations are much better than either of this method, leading to at least 10% improvement in terms of providing effective decision support. So we were surprised by that. So we also tried this alternative decision support method, which we call persuasive. This is something related to what I talked about earlier. I don't think this is a method that we should use in real life, but it's a way to evaluate model representations. So we show you the nearest neighbor in the predicted class, and then show you the farthest neighbor in the other class. So in this approach, we are essentially trying to manipulate, if the explanations are useful at all, I'm going to manipulate you to predict the model predicted class. And so it's not a neutral, that's why it's called a persuasive decision support. Again, I don't recommend using this in real life for any important decisions, but this can be a useful way to evaluate explanations. It's the same setup. We still ask you to determine the diagnosis based on which support image looks more similar to the original one. What we found is that in this case, AI starts become better. Like especially in the pneumonia case, AI became much better than what I showed you earlier. This shows that AI indeed learned some useful representations. The farthest one in the wrong class is indeed far away compared to the nearest neighbor in the predicted class. But somehow it's just in the nearest neighbor, it was not very well calibrated. So it was not useful in generating good neutral explanations. And still in this case, like our methods are very good. And in fact, in the butterfly case, we are almost like pushing close to 100% in this case. I should clarify this. In this case, AI models are super good. I think most of this work is about evaluating the quality of explanations. And if you just follow AI model, you can also get a 100%. So that's kind of a subtle way for me to admitting that we are still not achieving complementary performance in this task, but I do think in this case task, we are getting better explanations than we used to. Cool, that's kind of the core part of this work and this talk. And there are three main messages. First, we show that human-centered evaluations shows that current explanations fail to improve human decision-making. It's important to connect explanations with task-specific intuitions, and we show a case study in the context of case-based explanations for images. Since like our LHF is very popular, I feel like obligated I should kind of explain this a little bit just to clarify what is similar and what is different. I think in our cases, what we are collecting is human perception. Like we are trying to get your innate perception about which image you think is more similar than to our candidate image. And in human preferences, RHF, we are getting which one do you like better than the other. Although both are having this form of having two candidates asking you to choose one. but they're actually getting very different signals. Going back to what I said earlier, right? I think these are actually like very carefully chosen words. I think RLHF is focused on preferences, but in often cases, if you want to improve human decision making, what you really need to understand is human biases. And you need to understand like the mechanism of how humans make decisions, which was what the perception was about. So I think that was a kind of key conceptual difference in thinking about how we can build a complementary AI. And in other words, like this is a longer version of what I say, preferences are bounded by human understanding, right? It's driven by what you prefer. But we need more than preferences in this high-stake decision-making scenario, in policy, in science, and many other settings to be able to achieve complementary AI or complementary performance. And by that, essentially, I'm saying that we need to also understand the mechanism of biases. And that is kind of the concluding thing. I guess, I don't know, this is really more like a job talk style thing, but I don't know, I think this is still a vision thing which I really like, so I'm just going to do it. So I think human-centered AI has 3 important steps. First, I think we need to have better theories of human decision-making and the interaction with AI. And I think this is the part where essence is about studying humans, but we need to have a computational theory of humans, which I think is like a big part of computational social science. Okay, going back to the beginning part, but anyway, for people who care to be a computational social scientist, and I hope that you also kind of started to think about the problem of like human-centered AI in this context. And then with this knowledge, we need to reshape AI with new objectives, new data sets, and new algorithms. And finally, we still need to design and support effective interaction. Here is a very simple example. If we jump out of this earlier view where you have a human in charge of every single prediction, we have a framework called conditional delegation. Essentially, first, the human and AI collaborate not in terms of individual decisions, but in terms of identify what we call trustworthy region. Then for new examples, we will decide whether the example is in that trustworthy region, and if it's in that, then we delegate it to AI. If it's not, then we will maybe let a human decide or like do something else. And in this framework, we try this on content moderation. We are able, by some measure, to get a complementary performance. In this case, like human plus AI can get a much better precision in terms of identifying comments that should be moderated. Again, like I think if you're interested, you can dive into the details of this work. There's a lot of like subtle switch in terms of how we define complementary performance and what the task is defined. I think it's still very hard in the like original setup of this talk where you have human in charge of every single decision to have human AI complementary performance. In some cases, I may even argue that it may be impossible, but I like to believe that it's possible in some settings, and hopefully we have better theories that allow us to clarify what is possible and how we can achieve that. With that, I want to thank all my collaborators, and I hope that this talk gets you more excited about human-centered AI, and hopefully at least you remember this part of interpretation, which I think is critical for making sense of explanations. All right, thanks. I'm happy to take more questions.
So I'm thinking back on the first time you presented the kind of X-ray of lungs with a little box was sort of centered on the spine. And I just want to see if my take on that is anywhere near accurate. But my sense is that human plus AI did better just because the human had some knowledge that was not in some way encoded in the AI model, right? Which is that lung problems are usually not associated with the spine, they're associated with the lungs. So if that had been the model, then the human, it would have been a better model and the human would not have added anything to it. But the other part of it is that AI can sometimes detect relationships that we don't see. So maybe there is some subtle change in the spine that happens with pneumonia that AI could predict, so the human intuitions are just wrong. Is that sort of a summary of where this complementarity is or isn't? I mean, if the humans have accurate intuitions, they have knowledge that the model doesn't have, then complementarity is possible.
Yeah, I think that's accurate, right? Like that's exactly the gist of this. I think human need to have intuitions that AI doesn't have on its own, and that intuition can interact with explanations. Like somehow you assume that AI can generate explanations that tells you something prediction doesn't include, and that somehow like synergistically interact with human knowledge. I think that is a good summary of like what's going on. The only thing that I would add, like I don't object to anything that you said, which is totally correct. I think we also have some other work. Sometimes we call it model-driven tutorials. I think it kind of depends on what your assumption. I think it's important to think about human intuition, but human intuition doesn't have to be static, right? You can also have explanations whose entire goal is about changing human intuition. It's about teaching human knowledge about a task that they didn't have before. I think that it can also be kind of very useful direction for in the long-term version of like complementary performance. But like another comment about what you said is also like if you do assume that AI is perfect, it knows everything, then there is very little room for complementarity because AI is already like perfect, right?
Well,
Yeah.
I think what you have to assume is that the case that the human has knowledge that the AI doesn't is much more common than the case that the AI is finding something real that the human doesn't know about. It's much more common for the humans to have the correct knowledge than the AI to find something new.
Yeah, I think that's a fair, like, quick summary. Again, like, the subtlety is that like it doesn't have to be static, right? Like, ideally, the ideal case is that a human learns the right intuition that the AI has, and is able to use this knowledge to correct the wrong intuition. And that's a very high bar, and that's the most optimistic scenario. And personally, I'm not sure that can happen. But I think those are the possible moving parts that one can hopefully build towards. Yeah.
Have you looked at other kinds of explanations aside from this perception nearest neighbor based approach?
Yeah, I think like that was last year's work, and I think everything like is affected by GPT-4, like large language models. I think. Like for instance, I'm just like finding excuses for like why. I think like for instance, like in that example-based explanations, I think it's actually hard to adapt to text. That's something I thought about, and I haven't done that work yet, and I'm not confident that similar attributed judgments will be as useful. But one thing that I'm actively thinking about is like how to use causal explanations as a way to bridge the gap. Which like I think there's a lot more excitement on mechanistic interpretability, which is in some way, some sense causal, but I think that's different from being useful. I think most mechanistic interpretability are still follow the story of like opening the black box, which I think is critical for the sake of like understanding the models. Like again, that's a kind of good example. Right? I don't think it will be useful for the kind of goals that I'm thinking about here, and you need a little different abstraction. That's a problem I'm thinking about. I don't have an answer. Yeah. Yes.
So if you had the choice between an explanation generated by a human versus an explanation generated by AI, which one would you have more?
Which one do I like, it kind of depends on the goal, right? I think like a lot of what I'm talking about is that you are interacting with AI, so explanation of AI makes more sense. But I have other work that in general shows humans are terrible at explanations. So if you just throw that question to me at random, I would actually not trust the human explanations. But again, like it kind of depends on which human or not. But if you're interested, I have mostly that's just a short paper translating some psychology work to the CS audience. But I have a paper called on the diversity and the limitation of human explanations. So I don't have a lot of faith in human explanations in general. But again, I think like this is like there's a general statement. I think like in specific scenarios, like I don't know. If you have time, I'm happy to share more. But I guess like for instance, another classic example is that like most of you like in psych work, if I ask you like, can you explain why the car would turn on if you turn the key? Like most people, if you just ask that, would say yes, I can explain. But then if you ask them to actually explain, most of them will realize that they cannot. And you can think about whether you can explain that. At least, like I cannot explain that question. And I think it's very universal observation in most contexts.
Yeah, it's probably sort of related to James' early point that in your presentation, you talk about a scenario where by incorporating human knowledge and human decision into the training of AI, and then AI can have collectively a better performance. But I can also think of another scenario. For example, I play Go as a hobby, AlphaGo, and the first version of AlphaGo was trained based on human data. And then it's kind of, very good, but then they have a better version, Alpha Zero, which they try to remove human as much as possible. And it's only trained based on self-play against each other, like AI against AI. And they find it's much, much better compared to AI trained on human data. So how do you think about the difference between these two trajectories, and which, like under what condition you think which one might be working better compared to the others?
Like, again, I think a part of the issue is that working better is hard to define, right? I think if it's only about playing the game, and in the Go case, I think it's very clear that you don't really need a human in this process. I think that's a case where like it's unclear a human has more knowledge than that. Actually on that note, I think like Ping Kim actually recently is working with some chess professional working on kind of identifying the chess version of like what are the key insights learned in these chess engines that human chess experts don't know. I think that's kind of another set of like a very interesting work that's kind of related to this question of like changing people's intuition. But more broadly, like I think if the goal is to help human, then some version of human input is required at some place of the step, right? Even if we just train the AI entirely through self-play, but in terms of like generating explanations, it requires a human to be involved. You need to collect some knowledge about human intuition to be able to generate explanations that truly help humans. Otherwise, the explanations may not be useful for any human. I guess that's my take on that. Yeah.
In the slide where you showed random selection of like two X-rays versus the AI selection versus the AI with the extra triplet loss to like bring the embedding space closer to human intuition. The performance you were showing was the human decision making based off of that, right?
Yeah.
And so my question is, did adding the triplet loss to make the AI more human interpretable reduce the AI's performance or change it at all?
In this context, it didn't. I think one thing that I try to clarify later. I think in those tasks, pneumonia classification and butterfly classification end up being like very simple tasks for AI. But I think the reason we try those is that because the focus of that work is to think like just making some progress in terms of like having better explanations so that we can kind of get that out of the picture. Like whether you can really just trying to get people aligned with AI and aligned with ground truths are essentially the same. I think AI is like about 97%. So it didn't really change the performance there by aligning with human, but that's not generally true. We had a more synthetic experiment in that work where we tried to change the alignment between human intuition and AI and the task definition. And in general, even in that synthetic data set, I think the penalty of aligning with the human intuition is very small. Personally, I think that is a viable approach, but I'm not surprised if there are tasks where adding human intuition will ruin AI completely. It can really depend on the underlying alignment between them. Yeah.
I wanted to kind of ask about the inverse question, where I've seen before that like adding AI explanations make human predictions worse because of like anchoring effects and whatnot. So I was wondering, how do you avoid that kind of thing where AI explanations actually hurt human performance?
That's the point of the talk, right? Like I think we are trying to think about how to add AI explanations so that we don't hurt human performance and shoot for something higher. I see. So you are saying that you are in this kind of image where you are saying that human AI is actually here, even lower than human on its own. I guess that can probably happen too, but I think in that case, probably you can just remove AI. But I guess that, I haven't really studied that. Like I haven't observed that personally in my own work. Like I think that seems hard to resonate in the context of like categorical classification, since in most cases, like people would be biased towards AI a little bit, and that usually translates to a little bit of improvement compared to raw human performance. Yeah, go ahead.
Actually, I have an example of what he's talking about. Let's say freshman college students who are using ChatGPT for the first time for work, but they just copy and paste the output. So whether or not they get caught by their professors, right now I'm kind of saying if the ChatGPT is not really good at that area, their use of ChatGPT, which would be human plus AI, would actually be worse than if they did the assignment themselves.
Yeah.
Yeah, it's a good example.
I think that's a good example, right? But in that case, like the AI would actually be worse than human, and actually, okay, maybe the more effective way to answer that question, I think there's also like, I think I've been mostly focusing on the notion of human intuitions, which I think I show these images as my ending slide. I think this has been my focus, but like there are competing theories about why human plus AI is worse than AI, and one theory is cognitive dissonance. Like the main idea is just like people do not make sense of explanations actively. They don't even try. And I think that is kind of the scenario that could be happening in that example, right? Like once you have the AI written essay, the humans do not even do any filter, even if they can filter. And they have some more like kind of interaction design kind of work that kind of see how to encourage human to engage with explanations. I think that's another part of the story which I didn't get to at all in this work, in this talk. But I think that's a reasonable. I think personally, I think this is very important, and I think there's theoretical evidence to argue that this has to happen. But I think there are many other like interaction design or like psychological factors that can also be at play in terms of like what we eventually observe. Yeah.
You've mentioned that like it's crucial to understand human biases and perceptions when to make use of like AI explanations. Is there a set or a list of explanations, AI explanations, or some sort of guidelines that just make it more effective? For example, you've been using like the triplets. Is there anything that make it better for the overall goal of human AI complementarity?
Personally, like I guess that's what like I'm working towards. I think I'm not aware of like such guidelines specifically for explanations, but there are very good written like guidelines for human AI interaction. Those like I think literally there's an article called Guidelines on Human Interaction. You should check it out. But I don't think that those guidelines are about the kind of like task-specific intuitions. That like I think that's another kind of thing that I had this word task-specific intuition. I think that is what is missing in a lot of existing work. I think a lot of general work is trying to have this notion of like for instance, sparsity would be a non-task specific intuition. You can say like sparse explanations are generally preferred. But I think that alone is not going to change a lot of the argument that I'm making here. It's not going to introduce new connections between human intuition and the rest of the problem. And in order to solve this high-stake decision-making, or like at least decision-making that I'm framed in this talk, I think you need to have task-specific human intuitions, which just hasn't really been a common subject of study. And in every domain that I know of. But again, I think there's some outliers. There's some domain where there's more active work on. Yes.
Was there another question?
No, there was just another sound, which I was trying to determine what it is, but maybe you can start and then we can.
Sure. So I have a question. Like, when you say that in previous cases, the explanation provided by AI is not very helpful, when actually, human plus AI, the performance is degraded. But I'm wondering about the case where you really let the human learn. So you put a human in a long learning training regime just with the AI explanations that are not human tuned. Would you still expect to see the same degradation of performance, or would you expect that a human will be able to learn and pick up on what the AI is doing, and then use that to inform its decisions about the AI?
Just to be clear, right? I think degradation sounds a little. That's a very good question. I think degradation just sounds a little harsh. I think human performance is actually increased. It's just not complementary. I feel like that's a little more fair to what's going on. But I know what you mean. I think that hasn't been done a lot. Like I think I mentioned that we have this work on model-driven tutorials where we actually try to teach you what's going on, and that work is able to help human a little bit, but it's not able to remove this. I think that's actually what led me to kind of like slowly not doing more experiments anymore. I think there's something fundamental. I think what I explained in those causal diagrams still holds. Even if you learn a lot with AI explanations, you cannot really learn things about task decision boundary. Like at the minimal, to put it very simplistically, at the minimal, you should tell people what the true label is, what the AI prediction is, and what the explanations are. Then maybe that a human can start to learn that when the model makes explanation is such, and the model is more likely to make an error. I think that is the minimal process for it to happen. If you only show explanation and the model prediction, no matter how long you have to let people see this, it won't help people make a better decision. And whether the simple proposal that I just described would work, I doubt so, but I'm not sure that is sufficient, but I think that's at least opening possibilities. Yeah.
Have you ever manipulated the human intuition? Was like, for example, if my current level of accuracy is like this level, or the variation of the accuracy that I can originally, does it affect any performance when they collaborate?
That's a perfect question. That's a great question. Like I think we only did one such experiment in the second work. Like where we instead of manipulating, I think in general, I think if there's more work on manipulating human intuitions, I think that would be fantastic as well. We don't know how to do it. What we did was filtering. Like we had a trivial task on predicting income, and we have two important features. One is education, one is age. And then we filtered people based on whether they think age is more important or education is more important. Then we can show in this scenario, the results are aligned with our hypothesis, given your intuitions. So we have an experiment in the second paper on that, but that's a very synthetic or simplified setting. That's what made it possible. But yeah, I do think in general, knowing more about human intuition, being able to manipulate it sounds really bad. But being able to shape it it would be very useful in many contexts. And again, I think this is a very ethically charged area, right? I think it's unclear you should do those things in some contexts, even if you can. And that's another part of challenging of this work.
So I was going to ask, do you think it might be possible that we train explanations that are kind of malicious, that are believable, that are intuitive to humans, but are actually not good at the task? For example, in the triplet, in the loss that you designed, we kind of we encourage the loss to be lower for the human data, but actually higher for the task.
Yeah, totally possible. I think that's already happening. I think that's what LLMs do, right? And yeah, I think that's totally possible. I think I think it's unclear how you I think mostly I'm thinking about this cooperative case where how you can cooperatively improve human performance. But if you want to go adversarial, I think that's probably an easier path to take. And I think it'll be very easy to humans are just very finicky, and it'll be very easy to get them to do worse or trust things that they shouldn't trust. And so usually I'm thinking about the reverse direction, but I think insights in the negative direction is probably also useful. Just personally, I haven't worked on that, and I don't know. I'm not going to try to make the argument that no, I should work on that right now. But anyway, yeah. Any other questions? Any other questions?
All right. Well,
Great.
Thank you very much.
Thank you so much.
Very interesting.有一些
些是跟 interpretation 有关系的，所以是有科学的。We'll see. It depends on the target. Oh, I think we're discussing